Yesterday what we looked at were the remainder theorem and factor theorem. Today we're going to kind of build off of that and look at the Fundamental Theorem of Algebra, or better known as FTA, and we're also going to get into the rational root theorem for polynomials. So if we turn to page 15 back to our tree diagram, we're going to do the third and fourth branch here. The first one, again, first thing we're going to look at is the Fundamental Theorem of Algebra. Of the four theorems we look at in Math 3, I believe this is the easiest one because it is very simple. It tells us the number of roots slash zeros. Again, remember those can be used interchangeably. Function or polynomial has in both real and imaginary. The reason why I say it's the easiest is because the number of roots or zeros a polynomial has is equal to the degree of the polynomial or function. Okay, and then really quick review, you have your real roots. They cross, touch, intersect, whatever of those three words you want to use, whatever makes sense. Fill in the blank there. Your imaginary roots are always going to come in pairs. And again, just like imaginary friends, imaginary roots does not cross. You can't see where it crosses the x-axis. You have to use your imagination. Okay. So questions you're going to see asked is identify the number of real roots, and then identify the number of imaginary roots, and then to go from like a level 1 or level 2 question, they're actually going to ask you to find them. So the way you kind of complete those questions to at least get rid of some match choices, again, y'all have multiple choice tests. That's what makes it, again, very, very easy to use. Just graph, okay? Whatever they give you, graph it to first identify your real roots. Okay, however many times the graph intersects or crosses the x-axis, just take that, subtract that from the degree to get your number of imaginary roots. This right here works 99% of the time. The other 1% is multiplicity or multiple roots. Okay, we'll actually talk about those when we come to some examples that we see them. So, for example, I have this polynomial down here, so I need to tell number of roots or zeros. So how many real and how many imaginary. Okay. So very beginning of polynomials, we actually did brace maps to find like the different pieces, and we said that polynomials are named according to the number of terms in their degree. This is where us quickly being able to look at a polynomial, say it's written correctly, ascending, highest degree to lowest degree is correct. So if you can identify the degree, you're halfway home. Degree here is 5, so I know my total number of roots is 5. I then graph it, so x to the 5th minus 5x cubed plus 6x squared minus 14x plus 12. And again, cross the x-axis 1, 2, 3 times. Therefore, it has 3 real roots, and then 5 minus 3 tells me there's 2 imaginary roots. Again, this right here, if it is ever a odd number in an answer choice for imaginary roots, get rid of it. They always, always, always come in pairs. Okay? So again, imaginary roots come in pairs. Most important thing, number of roots total of a polynomial is equal to the degree. Real plus imaginary must add to get this number. So that's another strategy you can use. All right. So I then go to page 18. We're going to start on question 9. So I give you an example. Possible total roots. Again, I need to identify the degree. If I can find the degree, I have a piece of my answer. So 3, 2, if I don't have a number attached to a variable, it's an understood 1. And then my constant 0. So 3 is my biggest degree. Therefore, I'm going to have 3 possible roots. Now, identify how many real, how many complex. Well, we just go back to the graph and we type it in. K cubed minus k squared minus k minus 2. So this won't me to add a slider for k. That's because, again, graphing calculators, even Desmos, doesn't like variables beside x and y. So that's why I say just do y equals. And then from here, look and see how many times your graph crosses the x-axis. Once. So it has 1 real solution. 1 plus what is 3? 2. So there's 2 complex solutions. Rational roots, we'll get there in a minute. Alright, so in number 10, alright, try this one and see if you can write down or find first how many possible roots are there. Again, very quickly, 4, 3, 2, 1. Now I notice like this isn't equal to 0, so I need to work on this a little bit. That will allow me to put it in y equals, right? So the way I do this is subtract 34 from both sides. When I do, I have 10b to the 4th power minus 8b to the 3rd power minus b squared plus 62b minus 34. Again, biggest degree is 4. Now what I want you to do is tell me how many real roots, how many complex roots. Again, in order to find that, just go to Desmos and type the stuff in. 10b to the 4th minus 8b cubed minus b squared plus 62b. And then again, remember we subtracted that 34. And now we can see 1, 2. It crosses the graph twice. Therefore, we have 2 real. And then 4 minus 2, or 2 plus what is 4? 2. All right. 11, 12, 13, 14, 15, 16. Those can be extra practice if need be. Again, key takeaway. What was the difference between 9 and 10? If you have an equation, okay, we've already talked about this year. Equations have, stuff on the left, stuff on the right, but you see an equals to signs in equations. Okay, expressions, no equals to sign. All right. If one side is not equal to 0, you can't get just one graph without before making one side equal 0. Again, here is already set equal to 0, so I can just immediately go to y equals. Over here, I had to do a little bit of work. Sometimes we'll look, so like 14, 15, 16, for example, you would have to pick and choose what stuff you want to move. I like to keep it simple. I can move one thing here to make this equal 0, or I can move 4 things. Again, I work smarter, not harder, so I only want to move one thing versus 4. In question 15, what would you move? The stuff on the left of the equals or the stuff on the right of the equals? All right. See, I would move the stuff on the right because there's only 2 terms versus 3.